give some things up from herself that you should be able to just get a take. This is Alex from Moiya. Is it like just Friday and Saturday or something? Or... Okay, I'll look it up. I'm not sure if ever... I know, I knew about it. Yeah, I don't go to bed nearly enough. It's just like, it's just a real trek. How did you get here? You live in Brooklyn somewhere, right?
Yeah. I didn't realize when I got the second one, there were like 3 in a row that they didn't know.
Oh.
And so I
I've never tried to take the bus here. I'd like walk to the Elton. It's a long walk.
This is the front row. Good evening, Sunday service. If there's anyone still looking for a seat, there's a ton of floor seating right over y'all.
What?
So comfy.
Yeah. I think we should just take the chair. No one's been here for a while.
I'm Stephanie Acosta. This is Alexis Wilkinson. And we are the co-creators and programmers of Sunday Service. We are in our 3rd season and just starting to gear up for our 4th, so we will be back next season. We are the first Sunday of every month, and we choose an artist to play with curatorial structure as a way to use performance and gathering as designers. And there's more stuff on the website. Tonight, we have the incredible Janani Balasubramanian. Who'll be telling you a little bit about what they've got cooking tonight and who's working with them. We'll be taking breaks. Please feel free to grab more drinks. We are here. You are here. Thank you. And here we go.
Hello, my name is Janani.
Hi, Jen.
Thank you all for coming. Hello. I live with about 25% of the people here. No, really. That was JP Ventura on the... He's going to come back in the middle of the program to talk about both astronomy and music, because JP is 2 very awesome things, one of which is a DJ, the other of which is an astrophysicist. So, like Stephanie and Alexis said, I'm an artist, so I don't usually curate things. So when I was asked to curate things, I thought about how other people curate things. And I realized curating is just putting together things that you like. So I put together a bunch of things that I like, and that is this program. But for real, I want to take you back in time a little bit to one of my favorite writers, whose name is Italo Calvino. And I take kind of any chance I can get to talk about his work because I feel like there's a direct line between what I'm trying to do as an artist and today as a curator and what he did in the middle of the 20th century. So Calvino was a Cuban-Italian science fiction writer. He was also a communist and a Nazi resistor. He tried and failed at writing humanist fiction, where most of the characters are human, and figured out he wasn't really good at it, like me. And instead he started writing science fiction, where most of his characters are non-human things, also like me. So in his stories, he plays a lot with time. He often ascribes personhood to subatomic particles, and alligators and amphibians and dinosaurs and cosmic phenomena. And I opened the written description of this program with one of my favorite tidbits of writing from Calvino's work, Cosmic Comics. It's him describing the Big Bang. We were peering into the darkness, crisscrossed with voices, when the change took place. The only real great change I've ever happened to witness. And compared to it, the rest is nothing. So I've been returning to Calvino over and over again since the election. And not only because of the political messages that are sort of underneath his work and his science fiction, but also the ease with which he slips between different kinds of truth and different kinds of personhood, and the different transformative processes that have shaped the history of our universe. Since the election, I've also been thinking about how so many of us have clamped down on our particular version of truth. The same way that my dog holds his favorite chew toy, which is one that looks kind of like a spider had a baby with an ugly bear. No, but really, we've built this relationship with truth where we hold it very tightly and squeeze it, which makes sense because we have a government right now that is mostly built on lies and corruption. And I think that's a logical reaction to feeling that as a larger force. But I think there's actually something a little bit dangerous about that kind of relationship to truth, where we think it to be something permanent and fixed and unchangeable, where we think in terms of us versus them. We are the real deal, they are fake news. I think if we squeeze truth that hard, it can perish. Something else I've been thinking about, because I've been an artist with the Brown Dwarf Astrophysics group, many of whom are here, at the Museum of Natural History for the better part of the year. And there are so many things I learn just kind of being there with scientists, and I wanted to share a few of them with you. One is that science is not a set of cold and static facts. It's actually a community of debaters, a set of strategies for inquiry, a collection of questions. My favorite thing I've heard in our group meetings is whoever came up with the term exact science was not a scientist. I think that's beautiful and profound. Astrophysics, to me in particular, is a really patient, wonderful field where you have to see a celestial object or phenomenon 1,000 different ways before you can tell a story about it. I wish that we have that commitment to each other. To me, this is kind of what the whole evening is about. Letting those boundaries between our truths and disciplines relax and breathe and transform a little, so they can live nourished and prosperous lives. And when those truths and stories are ready to be replaced by others because of new data sets, it's a giant new data set that just came out, new people who come into our lives, or new social movements that we are then able to see those truths off with honesty and grace. My prayer is that we may all play at the boundary layers between art and science and storytelling and learn a lot and have a lot of fun. So with that, I want to introduce our first player, the Big Bang. I won't be reading bios because you can read them, and so that you can also spend your time listening to the art and science and inquiry. But our first speaker, first astronomer, is Schwab.
Hi everyone, I'm Schwab Abrams. I'm actually here to talk to you about an old data set and new things we can find in old data. So I study the smallest stars in the group that Janani was just talking about, the Brown Dwarfs in New York City group at the American Museum of Natural History. And I don't just study the smallest stars, but I also study the exoplanets that orbit them. In particular, I use this telescope that you can see here on the bottom left of the screen. This is Kepler Space Telescope. And tonight I'm going to tell you the story of how we find exoplanets using Kepler. And in this search, how we learn more about the stars that the exoplanets are orbiting and the telescope that observes them. So this story, the story of the search for exoplanets, begins kind of like a much more famous and familiar story. In the beginning, there was light. And which light is this? You can see here, above the plane of the Milky Way, a space in the sky that we call the Kepler field of view. So the Milky Way here is this stripe that's descending in light and color and shadow diagonally across the screen. And if anyone in the audience likes stargazing, you'll notice Cygnus the Swan there in the plane of the Milky Way. And the Kepler field of view is located diagonally in the upper wing of Cygnus the Swan, to the left of Vega, which is a very bright star, and a member of the constellation Lyra. The Kepler Space Telescope was launched in March of 2009 and spent its time for the first 4 years staring at this one spot in the sky. If we take a closer look, this is the first light from Kepler, a snapshot of the first data that came down in 2009. And so you can easily pick out a few bright stars, but if you look closer, you'll notice something that looks almost like dust, maybe mistaken pixels. Every speck is actually a star here, and those very faint specks are the smallest stars. And if we take a closer look, we watch this one spot for 4 years, we start to notice more about the characteristics of this part of the sky. It's a little bit like when you walk into a dark room, and at first you might not notice much at all. But when you let your eyes adjust, you start to notice the furniture and the details of the room. So this works exactly the same. We stare at this one spot in the sky over 4 years, almost continuously, collecting each little bit of light, each photon, so that we can learn more and more from this light. Because in astronomy, light is all we have. And so if we do this, you'll see in this visualization by Dr. Ruth Angus, we notice that over the 4 years, the stars appear to twinkle. And this is not because of an atmosphere between us, because Kepler's launched into space. Instead, the stars are actually brightening and dimming over time. And this is sped up, where 10 hours passes in a second as we watch this. And some of the stars seem to brighten and darken periodically. Some others seem at random. Some almost turn off entirely. Some dim just barely. But there's something hidden here in this light. And so we can ask, what's going on? Why are these stars brightening and dimming? And there are many reasons. But the reason that's most lucky for us exoplanet explorers is that if a star and its planetary system are positioned just right, the planets will pass in front of the star as we view it, and dim the light of the star just a little bit, as you can see these 3 dark planets in front of the star, where we see them in shadow. And so if we look, this is a nice visualization of this. Here's a planet passing in front of the star. we can track the brightness of the star, and as soon as the planet starts transiting the star, you'll notice on this plot on the bottom, there's a dip in the star's brightness over time. And we can measure this dip and learn things about the planet, and learn things about the star, and how the planet is related to the star. We call this type of plot on the bottom a light curve, which is basically a description of how bright a star is over time. So this might cause us to modify the introductory sentence of our story. We started with a story of the search for exoplanets, and we said in the beginning there was light. But it's important to note that in the beginning, from the very beginning, there was both light and shadow. And so if we look back at that video of all the stars twinkling in Kepler and focus on just one of them, we would guess maybe the star has a planet or two, so we'd expect to see that flat line and the dips coming from the planets. So let's take a look. That's what we see over time. So it's hard to, looking at this, does anyone here specifically see a planet? Maybe, it's very hard to tell. And so it turns out that we have to go back and modify our beginning sentence one more time. In the beginning, there was light and shadow and noise. And that's where I come in. I study the noise in Kepler light curves. And in this study, I have found something interesting. I have found that the noise itself contains both beauty and knowledge. That as much as we learn from the light and the shadow, we learn from the noise as well. So I'm going to explore a few aspects of different things we can learn from noise, but I don't know, noise is beautiful. There's so many things to learn from it. So here we're focusing on one star, and this is a dwarf star. So you might look at this video and say, wow, that's an extremely pixelated star, and you're correct. This star is so small that it takes up barely more than 1 pixel on Kepler's detector. And you'll notice over time it almost seems to jump back and forth. It's hard to find the edges of this star. So instead of trying to find the edges of the star, we look for the centroid of the light. We add up all the light we can collect on the detector and find the center of that added light. And so you'll notice this tiny little red dot jumping back and forth, and that's the centroid. And if we track this motion in both side to side and up and down, you'll notice here on this plot, side to side is plotted in blue over time, up and down is plotted in red over time. We get this beautiful pattern, and it seems to repeat over time. And that's curious. Why would it be repeating? Another funny, completely random thing, which Janani pointed out to me and I agree with, is that it kind of looks like Dixie cups, if anyone had Dixie cups. It looks a little bit like that. Not intentionally, but it does. And so we can ask, why does this seem to repeat over time? Is this something about the star? Is the star moving in a certain way that causes it to slide back and forth on our detector? So it turns out that it actually isn't because of the star, but it's because of Kepler itself. And so this is a nifty video from NASA, where you'll notice Kepler orbiting around the sun. And so we launched Kepler so that it orbits very close to Earth's orbit around the sun. And watch over time that Kepler seems to shift 4 times out of the year, just twisted. It's going to twist again, and again, and one last time. And so throughout its yearly orbit, it twists. And it twists for 2 reasons. Every day, every minute, every second, Kepler is monitoring, making sure it's keeping its position on the same field of view, so it could stare at the same one field of view. So there's a constant shift over time. But also those 4 distinct shifts over the course of the year are protecting Kepler from the sun. Kepler has this kind of asymmetric protector, and as it travels around the sun through the year, it shifts its protector, so the protector is always facing the sun. And so if we look back at this plot, we'll notice that the position is always changing over time, but there's these 4 repeated parts of the pattern, very closely repeated parts of the pattern, and that's for the 4 years that Kepler observed. But within those 4 years, there's kind of these 4 shapes, these diagonal lines and these curves. And each curve corresponds, and diagonal line corresponds to one of the twists of the telescope, which we call a quarter of Kepler's data. So each of the 4 years is divided again into 4 each year. And so each quarter repeats 4 times on this plot here. And so Kepler has that daily motion and that motion that happens 4 times a year, but it also just has the same motion as Earth, this orbital motion around the sun. So once a year, it repeats itself. It goes back on over itself. And so this causes an interesting relativistic effect. It's called velocity aberration. And it actually turns out that when you're moving fast enough, things that are stationary and not moving appear to move toward the direction of your motion. And so when we're looking at the Kepler field of view and the Kepler telescope itself is zooming around the solar system, the Kepler field of view also seems to shift, so that when Kepler's zooming this way, the field shifts that way. And when Kepler's zooming back this way, the field shifts that way. And so we can pick that aberration too out of the data. And it's not surprising that the aberration then is periodic, because the orbit itself is circular and periodic. And if there's anyone in the audience who loves math, I know I do, you might say this reminds me a lot of a sine curve. And we can model it with a sine curve, which is really awesome, because we know sine curves well, so we can measure the days between one peak and another peak of the sine curve, or a wavelength, and then discover the full year of Kepler. So we know ourselves that on Earth, we orbit in 365 and about a quarter days. Turns out Kepler has longer years. The year of Kepler, which you can now measure from this velocity aberration, is 371.72 days. So it's slightly farther out from the sun than we are. And if you like birthdays, I like birthdays, you could celebrate your Earth birthday and your Kepler birthday. Why not? So there's a lot of noise. I like to say there's this wild rumpus of noise options. So sadly, I don't have the time to go into all the beautiful plots we can pull out, but just another few of the major noise contributors. At the top of this plot, you'll see someone who's actually building the digital detector for Kepler, which is known as a charged coupled device, or CCD. And CCDs are great because they take light, they take photons, and they translate them into electrons, which we can then process digitally. So we can now get this digital data from the actual light. But one of the downsides of CCDs is that they are very sensitive to temperature changes. And so throughout the year, as Kepler orbits, sometimes it's a little closer to the sun, sometimes it's a little farther, it turns towards the Earth every once in a while and downloads data. And so the heat changes a little bit. And so heat also adds noise into the light curve. And it's not only the instrument. All 3 examples we had so far were instrumentation examples, how the telescope itself added noise. But there are astrophysical sources of noise too. So down on the left here, you can see a visualization of something we call cosmic rays. And these are highly energetic particles that are ejected from catastrophic events like supernovae or faraway galaxies that have something called active galactic nuclei, which is kind of like black holes turning the stars around them into hot mush. And it's pretty awesome. And on the bottom right here, we also see some of the stars are highly magnetically active, which cause these bright flares and sunspots, so that when the stars rotate, some of the sides are brighter than others, which also add periodic dimming and brightening to the light curves. And so all of these light sources needed to be looked at and understood. But if you look at these light sources, if you stare them in the eyes and try to understand them, you can model them and remove them from your light curve. And when you do that, you actually find some interesting things. So once we do that with this specific light curve, we look at its noise and we model it out. Ta-da! We find that there is actually hiding in that noisy light curve an almost Earth-sized exoplanet. This exoplanet is around a small star, and it's about 77% the size of Earth. And so it's close enough to the star that it might be warm enough for light, but it's hard to determine its exact habitability yet. We need to look a little closer, and we're going to look back at some of that noise in the light curve. We're going to try to understand particularly the magnetic activity that we can pull out from noise, from what seemed to be extra, because that in turn tells us more about this planet too. And so in the beginning and in the end, there remains light and shadow and noise. But it turns out that they're all important to understand the universe around us. Thank you so much for listening. questions, by the way, please feel free to ask.
Come talk to Elliana. Thank you. Yeah, so now I'm gonna hand it off to JP. He's gonna talk about music and astronomy.
Okay, sweet. Is it right? Following?
Yeah.
Good morning, Eddie. How's this work?
I got you.
Technology.
This one.
Oh, wait. What's up?
Yep, no, I know.
Oh, okay, good. Sweet.
All
Hi, everyone. My name is JP Ventura. And I'll be presenting about a project that I've been doing for the past couple of weeks, sonifying data. I'll get into the particulars of what that means. Okay, so a bit about me. That's my name. I'm a physics and earth and atmospheric science major at CUNY. CUNY. And research intern at the American Museum of Natural History, which proved that was mentioned before, BDNYC. Like that. And okay. Wait. Anyway, so I have a non-traditional path in science and in school. For a couple of years, I took a couple of years off and I picked up DJing. First, I took a couple of classes at a place called Scratch DJ Academy, which used to be on 6th and 9th Avenue. It's now by Cooper Union. But it was actually a DJ school started by Rep. Brum himself here in 1983. So it's pretty cool. He just wanted to teach the children, as they say. Oh, yeah, thanks. And yeah, so I tutored kids anywhere from 6 to 15 years of age on how to mix particularly house music. And house is a huge umbrella, so that involves like EDM type stuff. I like classics. It's a little ballroom. And we got a bunch of silliness, and a lot of broken equipment, but also a lot of hours of good fun. So, data application. What the fun? Wait, what is that? Wow. Anyway, it didn't come up. Anyway, let me explain for you. So, it's a process of mapping aspects of data to the production of sound signals. It's an academic and artistic endeavor, and so I delineate, and I mention this because there's a lot of work that goes into establishing standards of what sonification should be as far as actual mathematics and signal processing. Scientists are doing this a lot now, not in their artistic domain, but to reveal other insights into data as opposed to just like other insights that we can get from sound that we may not be able to get from looking at a plot. What's also awesome about this is that it's also an endeavor that's taken on to increase accessibility in the field for non-sighted astronomers, of which there are many. Time series data is particularly well suited to sonification because we can map sounds to musical notes, and this evolution in time is something that really aids in understanding the difference between a signal that we get at one power or another over a unit of time. So any data that we have, particularly as astronomers, Ellie was just talking about light curves, these are taken over a series of months, are well suited. And these applications of sonification are built around, oops, sorry. Wow. Something that's called parameter mapping. And so data, in effect, in its most simplest sense, is just a matrix of numbers. It's a table of numbers. And these numbers can be put on some sort of continuum and mapped against things like pitch, duration, onset, which is kind of what having you hit, a note, and so on and so forth. So Ellie mentioned light curves. This is what I have also sonified, also for a Kepler object. But it's a graph showing the variation in light or brightness received over a period of time for a variable star or another body. It's not just stars that do this. It's not just stars that change in brightness over time. Galaxies also do it, another host of astronomical objects. But I'm a star guy, so yeah, I sonified some star stuff. So just a quick science bit. The reason for this variation when it's not a planet is actually that you have the dense core where you're fusing two hydrogen atoms four hydrogen atoms to yield one helium atom. And when you fuse that under immense temperature and pressure that you would find in the stellar core, it releases an enormous amount of energy. So that energy, in terms of coming from the mass yield using EMC squared, is about 426 million, million tons of photons. Oh, not photons, but photons don't have mass, but you can convert them. Anyway, it's this weird physical thing. It's a lot of stuff. But what ends up happening is that these photons are trying to escape. And sometimes in stellar exteriors, they can be a little dense. Astronomers call them opaque, and they won't let the light come out. So what ends up happening is that it bunches up, it sort of expands, and then the outer layer sort of decreases in volume and density, and that light can escape. So for us astronomers, when we're looking at it, we see a corresponding brightness in the light curve. And then when it sort of settles back down, you see a dip. It tells us about the dynamics of the interior. So another bullet, it's probably not going to come up. It also helps us calculate distances in space, in the Milky Way particularly. The regular sort of frequency or beating or dimming of a star, we can use the time component of that to back out some distance. So I'm looking at Tabby star. This is a Kepler star, KIC 8462852. It's named after Tabitha Boyajian, who is a professor of astrophysics at Louisiana State University, who first discovered the object. It's got a weird light curve, and so the light curve, we're all in. Well, what's going on? Sorry. The light curve is really of interest to astronomers because it's not periodic, it's not regular. So it's not a planet, it's not a pulsation. So the first thing, which was sort of aided by the help of the public, was aliens. Now, what was initially kind of like the reasoning was that it was proposed that there was a Dyson sphere around this object, or what's also known as an alien megastructure. This is a term popularized by an astrophysicist and mathematician, Freeman Dyson, in the 1960s, which in his description was a way of technologically advanced civilizations to harness the energy of a star for, I don't know, advanced technologies. So it turns out that's not what it was. We found out that it's actually much more likely, I mean the studies are still being done, it's much more likely that they're actually huge plumes of vaporized comets that are orbiting this star. So this is Tabby star. This is the light curve. Now this is sort of in some weird unit. It's BKJD, Julian date, some astronomer time type thing. Normalized flux, which we can take to be brightness as percentage of the total magnitude. And this period of observation was from January 12, 2013 to April 8, 2013, so a couple of months. First of all, you can see that the dips aren't periodic. There's no sort of regular frequency, no sine-like behavior. And also this huge dip right here, which is about a 20% dip in this brightness. Anyway, to get to the sonification, I've sonified this data by mapping all of these values to musical notes. These can be matched to frequencies, or otherwise known as pitches. And I've inverted it. So I'm going to play a sound clip for you of what the sound of a light curve sounds like. But notice that when you hear particular differences, the pitch will go up, so it'll sound higher, but it's actually a dip in the light. So I've also taken this data and used it artistically. So I didn't use the entire light curve, but I've taken slivers of this sort of predominant magnitude that you've seen in it and created in my own sort of song from it, dubbing it with some samples of other things, adding some cool effects, just wanting to sort of make like a cool space song for you guys. But yeah, this is sort of the end, but we're going to listen for a couple of minutes, and I hope you enjoy. But I wanted you guys to sort of paint the image for yourselves. But that sort of basal, like string sound, that was the predominant magnitude of the light curve. You would often hear those were the three peaks that you saw in the light curve. And I added sort of the boom, 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 just to sort of be reminiscent of this pulsation. It's not going to be at this star because it's not a it's not a variable star in that sense, but it's all sort of just to sort of invoke feelings of being among the stars, being among variable stars, sort of walking across the cosmos. So thanks again.
All right, next is Mark Popinchalk, who's somewhere. Oh, there you are. We're going to talk about the transformation of the universe.
Thanks. Wow, thank you, everybody. First of all, let's give another round of applause for our first two speakers. They did a fantastic job. Also, huge thanks to Janani for putting on this awesome show. I'm having a great time. Yeah, so I am, that's, again, JP, this is my name. I saw you were showing up your name too, this is my name. I'm a grad student at, first year PhD student at CUNY. I also work at the American Museum of Natural History. I'm part of the Brown Dwarf New York City group as well, so you found the trend, a lot of us are from that group. And so I'm going to be talking about how astronomers try and understand, astrophysicists try and understand how things change over timescales that are really, really big. I'm going to be using two specific examples. We're going to look at how stars evolve in their lifetimes and how galaxies combine, how they merge together. And so some of the things we've actually already kind of talked about that are kind of fast astronomical processes, right? Exoplanets, the examples we saw before of them passing in front of their stars, a lot of those planets are very close, so they can orbit once a week, or maybe not once a week, but they're quite, well, some do want to go once a week, but they're very quick, right? They happen within a year, within a month, and something like quasar activity, which is something supermassive black hole in a galaxy, it's consuming stuff all the time, and it can change on similar timescales. Even, I put black hole mergers in here because maybe you've heard of gravitational waves in the news. That was a big finding, and that when they actually merge is a very quick, sudden event. You say the best, a good experiment for scientists is something that can happen in their lifetime, which is why a lot of the spacecraft that go out to other planets, you kind of really need to happen to get to those planets really quickly, because you don't want the scientists who designed those spacecraft to have died before they get there, because they want the credit when they get there, right? They want the prizes of sending that thing there. So that's science for you. So when you have these slow astronomical processes, like how a solar system forms around a star, or how a galaxy comes about or merges with another one, or even the big cosmological questions of how does the universe begin or how does it end, how do you answer those questions when you can't set up an experiment that's going to end in your lifetime? Or more conveniently, you can make an experiment that runs every day or something. How are you going to be able to try and solve these things? And so the first thing I wanted to do is, this is how they do it. They either can combine many individual observations, so looking at lots of things that are in the process of these transformations, so look at a bunch of different stars and see how each one is, or try and get something from looking at them all together. Or in the age of computers, you can run simulations and try and create your own universe or create your own galaxies and merge them. And we're going to do some examples of this. So I wanted to start with some stars. And this is a great video from the ESA, the European Space Agency. And I'm going to quickly explain what's going to happen. Is we're going to zoom in on a field of stars. And this is an actual observation of a cluster of stars. And we're going to eventually make a little plot out of just moving them around on the screen. And on the lower part, we're going to just arrange them from left to right by their color, and top to bottom by how bright they are. Oh, no, that's the laser. I just lasered, pointing the laser at somebody else. Jenny even warned me not to do that. I'm sorry. So you can read this if you care to, but the main point is this Hertzsprung-Russell diagram we're going to come back to. This is essentially what we're making right now. We're making this plot that has existed in astronomy for a long time. And so this is a big field of stars, and we're going to zoom in on it a little bit because there's too many stars to look at once. And we're going to zoom in and zoom in and zoom in. And the color, I think, is, I'm not entirely sure, but I feel like it's exaggerated a little bit in this. But we have some red stars, we have some blue stars, so let's arrange them. So all the red stars are on the right, and all the blue stars are on the left. It's super convenient. And then, but this is all real data as well, right? And now we're arranging them by their brightness, okay? So the brighter ones will go up to the top, and the dimmer ones will go down to the bottom. And we see something emerge. We see something, right? This is all real data. These are all real stars. And so we can see some things, we see some trends. This is called the main sequence. We'll talk about all these in a moment, but let's introduce the names. Red giants, and blue giants. And so these are all stars in their own lifetime, right? They're going through the process of their life, but by combining and looking at all of them together, we can kind of make a trend. And then we put them all back in their place so that they can go back to where they were before. Great. And so we look out, and it all looks very complicated, but if we take lots of data and we look at them, we can make this trend. And so now we'll look at a cartoon of one of these Hertzsprung-Russell diagrams, which doesn't look nearly as good once we see all the stars move around, you know, it's way more convenient that way. And so don't worry too hard about the axes here. Basically, again, we're arranged by color on this axis and by brightness on this one. And this is that main sequence we saw come out before, this kind of path right here. And this is the main, it's called the main sequence because the star will spend most of its time on that sequence, right? So let's take a step back. If we're an observer, we see all these stars, we can make this plot. What does it mean? We still have to kind of explain it. And the way we do that is, luckily with stars, you're able to apply a decent amount of mathematics and physics to it. It's not the most simple problem, but you are able to do that. And you can kind of figure out how it's going to advance. And so our sun-like star, right now, is sitting here on this main sequence. But at some point later in its life, it will go up to be in this red giant area, and it'll be at a different part of the diagram. So that picture we saw before of all the stars moving around, all the stars were in different parts of their lives. But we could combine them together and get an idea. We have to go back and do some math later, but we can get an idea of how it's all going to play out overall. The brighter or bigger star will be at a different part of the main sequence, and it will follow this line over here into a slightly different section of the diagram. And similarly, the further up you go, it'll go off into all these different paths. But the point is, by looking at all these stars combined and doing some math later, we can figure out how these stars evolve in time. And the lifetime of the sun is something around 10 billion years. But we've plotted it out right here. These stars are a little bit, their lives go a little bit quicker, maybe 10 million years or something for the really big ones. But the point is, we've successfully made an experiment or made a result, and we didn't have to wait 10 million years to do it, right? We don't have to watch one star live for 10 million years if we can look at 10 million stars for 1 year. Okay, so now let's go to galaxies, because galaxies are pretty. And I put this as the background for all my slides. It was really annoying because this galaxy is in the way of all the words, and it just contrasts. It's poor. Look, you can't see that it's messing with the bees over there. Anyway, we're not looking at stars anymore. Now we're looking at galaxies. Okay, every single one of these. I mean, this one is a star. You can tell the stars out by this diffraction pattern right here. It's got a shape like that. I think there's one more over here. These are all galaxies. Okay, so now it's not just one star. We've got billions of stars and billions of stars combined into a big mass of stars. And we can already see that there's some differences between them. We've got different colors here, different colors there, much like with the stars that mean something. But I wanted to just give you a perspective of how big this is. This is from the Hubble Extreme Deep Field. They call it HXD DF because they don't want to. They want to use the X, not the E. They want to seem extreme. So if you look up at the night sky and you see the moon, this is how big it is to scale when you look up in the moon. And this is how big this picture that we were just looking at is up on the night sky. And it's in a pretty dim part of the night sky. So it's something like if you hold up a dime, I think I've heard that said, if you hold up a dime at arm's length, it's covering that much of the night sky, right? And so you have to put a dime there, and a dime there, and a dime there, and then you can get all the galaxies. But look how many there are just within one dime of the night sky, right? I didn't think I was going to be using dime as a unit of measurement tonight, but there we go. So the point is there are lots and lots of these galaxies, and you can observe them, and you can observe them for, they've been observed for many years, and so almost 100 at this point. And so how do you classify them? How do you try and give some order to them? Edwin Hubble is one of the first scientists who came up with a classification scheme, and they basically said, all right, if they look elliptical, we'll call them ellipticals, and if they look spiral, we'll call them spirals. You know what? Some of these spirals have a bar in them, so I'll call those SB, spiral bars. And there you go. Now, careful here is, like with our Hertzsprung-Russell diagram, when we were looking at the stars, we could see them in different parts of their lives. That's not the case necessarily with galaxies, okay? It's not, you don't start over here and then end up on one of these two paths, or one of these two paths and end back necessarily. When they merge, they might change their shape or something, but the idea is that this isn't an evolution in time. This is just a way for us to classify them, okay? But you get more complicated with how you classify them. So here we have those ellipticals and some spirals and some spirals over here, but we have intermediate spirals, we have irregular galaxies. You can take that idea and keep running with it. But the main idea is we have these elliptical ones right here. And again, remember, if there's a diffraction pattern that is one of the nearby stars to the Earth. And important thing with ellipticals is that the color here isn't very blue. It's quite yellow and red. And that's because the stars in them are mostly yellow and red. And so that means they're quite old stars. There aren't the new stars. If there's a new star, it shines blue, it shines bright, and it dies. And it goes away, and you lose that light. Or you lose that color represented in your light. Versus, say, spiral galaxies like this. This is the pinwheel galaxy. And here we can still see some yellow there, sure, but we've got these blue regions here. And that means there are stars forming. They are young stars, and they are giving off their blue light. So we can classify these things. We can talk about some of the things that are going on inside of these galaxies as well, why they look the color that they do. So stellar feedback is something, we'll talk through all these. Why don't we just go through them? Great. I'm going through a different order than I wrote them in that last slide. The idea is that as angular momentum, I say that here as in when these stars, this is the sun here, this is not a real picture of the Milky Way, this is a representation of it, because you can't take a picture of something that you're in. It's like if you're inside the bus, you can't tell what color the bus is on the outside unless you got in the bus first, which is hopefully what you did. But we started inside the bus, so we don't know what it looks like from the outside. And so, we do know that we're a certain distance away from the bulge, and we do know that we go around about every 20 million years, and we kind of go up and down above the disk of the spiral every so often as well. And so basically, again, these are all groups of stars, and they're all moving around, right? There's these internal processes of these stars moving around. They have stars being born all the time. If they're spiraling, there's still maybe some star formation ellipticals. But this is a famous picture from Hubble of the pillars of creation, and essentially this is a big nebula of gas, right? There's tons of gas, and you need gas to make stars. And if you look at any one of these little spindles right here that's coming off of these things, that's most likely a star being formed. It's about to emerge from its gas cloud and go flying out and be very, very bright. And however, the bad thing about that is that when you have these stars that are big and bright, especially the really big ones that we were talking about earlier, the blue ones, they can go supernova. And when they go supernova, some of you might not be able to see, but there's a big bright light right here. And when they go supernova, they give off more energy over the course of a couple of weeks than they outshine essentially the whole rest of the galaxy. So an individual star outshines a billion, or a couple hundred billion. So what that also does is it expands that gas, and it shoots off a lot of the gas that's going on in the galaxy as well. And so you get kind of a negative feedback. If you have a lot of stars forming, they can also blow away that gas and then prevent other stars from forming. The point of all this is that there's a very complicated process of what's going on inside these galaxies. Let's make it more complicated by combining, or putting them all in space together. Okay, we don't have an individual galaxy now. This is a big cluster of galaxies. We've got ellipticals, we've got spirals, we've got everything going around. And they're going to eventually, some of them are going to merge together. And this is a really cool image of two spiral galaxies in the process of merging. And so how can you understand how these things collide when you can only see a single snapshot of this merger when it's going to take billions of years to finish? Well, what you can do, no signal. This is fun. I'll be the galaxies. All right, spinning around. No, we'll figure this out real quick. But what you can do is you can do the same thing that we did with the stars. We're going to look at a bunch of individual examples of these mergers and see if we can tell something from it. But we also, we used the math. Ooh, this is a really cool view. We used the math before to tell us about the stars. Luckily now we have computers. Don't worry, the next slide doesn't really have any pretty pictures on it. We can use computers, and this is a paper from the 70s of one of the first times that they really could use computers, and this is them trying to show how galaxies merge. So we're basically making a model of it now. This is the kind of other way to show these long time scales. And there's basically about 300 or 400 groups of stars in this galaxy. And they just put a big mass swinging by it, kind of like another galaxy, but the computer's not good enough to show stars for all of them. This is exciting. I'm really excited. So I'm going to show you guys so many cool things. Okay, there we go. Yeah, let's give it up for the tech. So we have all the stars coming around from this one galaxy, and then this is essentially another galaxy in mass, but they just don't bother putting any stars on it because it's the 70s, and you're essentially using a toaster to compute these things with vacuum tubes in it. No, so let's fast forward 40 years, and we've got, and it really is 40 years because this is a simulation that came out in 2008, and essentially we're going to have two spiral galaxies. This is a really cool video of two spiral galaxies combining, and as we run the simulation of these two galaxies combining, we're going to rotate it in freeze frame and put in images of actual observations to show you again, just, I'm going to stop talking because this is, let's keep going. Actual observation. Yeah, this video blows my mind every time I see it. Oh, there's one more, great. So again, we're not seeing an individual merger happen over the billions of years, but we're taking our best guess from simulations and matching them up to observations, which is the definition of our best guess, right? Our best guess has to explain everything we see. And we're simulating billions of stars. I don't think we're necessarily simulating billions of stars in each of those, but this came out in 2008, so I'm sure even now they could make even better simulations. But I guess I wanted to end on is that I can see this is transformations on timescales that are longer than we would want to make scientifically, but there are transformations even in our own lives that happen over timescales that we're not necessarily aware of. And I'm not saying you should simulate a person and have them go through to see how they change, because that just sounds like having a child, and I don't necessarily want to have a child right now. But there are a lot of things that you can definitely make some similarities here, right? We kind of observe ourselves or our peers on a snapshot, like just in one instant. And maybe you can say, oh, I've changed so much since this earlier part of my life, but that change happened over a longer time. And even with all these internal and external processes, which one of them are going to dominate and which one of them are going to change you the most? I don't have an answer to this slide. This slide was kind of thrown in at the end. But I'd like to thank you all so much. I had a lot of fun speaking with you.
All you astrology lovers, it's not me, but it's for all of you. But I love Moiya's talk anyway, so this is Moiya McTier.
Hi, I'm not part of the BDNYC group, but I do think brown dwarfs are cool.
We wanted you.
I'm sure at least one person in this room has opinions about astrology. As someone who has studied both astrophysics and folklore in an academic setting, I have really strong opinions about astrology, and so I'm not trying to change your opinions, I'm just trying to share mine with you. So astrology probably conjures some images or ideas in your mind when I say it. You may think of horoscopes, you may think of a newspaper clipping that tells you when you should eat certain foods or when you will and won't find love in the world. But that's not what astrology always meant. If you go back 1,000 years or more, astrology was something that people used to predict weather patterns or tell farmers when they should plant certain crops. Really, astrology meant understanding how space influences your everyday life, because it does. And so that's what I'm going to try to convince you of. So I want to tell you what I think astrology can mean, because in college I spent a lot of time thinking about the intersection between astronomy, space stuff, and culture and folklore and the stories we tell each other, the stories we pass on to our children. But maybe you don't want to call that astrology, maybe you want to preserve the meaning that you already have for astrology, so I'll give you a new word. Exolore. I'm still working on it, it's not perfect, but I think it does an okay job of encapsulating this idea that I've come up with. And so I really think about this in the context of exoplanets, which Ellie gave a fantastic introduction to. So this is actually an old image. I wrote the number on my hand, but we have found way more than 1,000 exoplanets at this point. We have found 3,725 planets that we have confirmed are exoplanets, and there are thousands of other planets waiting to be put through the pipeline, and scientists say like, yep, that's a planet. But planets are all different. They have different atmospheres, they orbit different types of stars, they're made of different things, they're different sizes, they have different masses. No one planet is like another. It's like a snowflake or a fingerprint. And so what I like to think about is what would life be like on those planets? What would the biology of the life that forms there be? What would the culture of those life forms be like? And because I have studied these two seemingly very different fields, I think I'm uniquely positioned to think about what the culture on those planets would be. There are lots of different scenarios. Like I told you, all of these planets are different, so I'm going to talk to you about one scenario today, and that scenario is tidal locking. Can everyone see the little animation down at the bottom? I don't know if you have to, okay, good. So tidal locking is a phenomenon that happens on a lot of different size scales. So our moon is tidally locked to the Earth, but planets can also be tidally locked to their stars. And what that means is that one side of the planet would always be facing the star. So you would have a day side and a night side of the planet. And you can imagine that life that forms on that planet would, on different sides of the planet, would develop different biology and different cultures. And so I'm going to explore that, and we'll explore that together. First, a little bit about the biology. Our eyes on Earth, our human eyes, evolved to see the best at the peak of our sun's spectrum. So a spectrum is a measure of how much energy the sun emits at different wavelengths. And I don't know if you know this, but our human eyes have evolved to see green light the best. Have any of you ever used night vision goggles? Yeah, it looks green, right? That's because human eyes are best at seeing green light. And that's because that's the wavelength where our sun emits the most energy. So the eyes of this life form that exists on this planet would probably evolve to see best in a different color. On the night side, they might not evolve eyes, they might not form eyes at all. If they do form eyes, maybe they don't use them in the same way we do, but vision would be different on the different sides of this planet. That's what I'm trying to tell you. The stuff that their bodies are made of would also be different. I can imagine that on the day side, they might have really thick skin to protect themselves from the harsh sun, which is always beating down on them. They don't have any cool nights to take a break from the heat of the sun. But maybe on the night side, they have fur, something to protect themselves from the cold. None of this is exact, by the way. I really liked what you said about exact science not being real. But this is just my best guess of what could possibly happen, like what dominoes would be knocked down given the initial conditions on this planet. But culture is what I am really interested in. I didn't study biology, I studied folklore, I studied stories. So what would the stories be like on this planet? Well, one, because time goes into stories, both sides of this planet would have distorted concepts of time, but they would be distorted in different ways. We measure days and weeks and years based on how the sun appears to move in our sky. But if you are always looking at the sun, how would you measure time? There wouldn't be years, there wouldn't be days. So you would have to come up with a different way to measure the passage of time. On the night side, they never see a sun at all. Maybe they measure time by how the stars move, but stars move really slowly. So I can imagine that on the night side, all of the life is really patient. Maybe it's much more like the Midwest than New York City. But these would influence the way that people have to measure their time. Second, maybe you don't think about this, but your holidays, the rituals that we do as a society they all come from astronomy in one way or another, or most of the major ones do. Halloween, Christmas, Easter, Hanukkah, they all come from the changing of the seasons. If you live on a planet that doesn't experience a change in seasons because the sun is always beating down on you, or you never see sun in the first place, you would have different rituals, you would have different holidays. So I have absolutely no idea what the holidays on the day side would look like, but I can imagine that on the night side, maybe they have holidays that are about meteors coming. Imagine if we had a holiday based on Halley's Comet. And I think that's what this side of the planet would be like. The mythology, the stories on this planet would also be very different on both sides. So the day side would have a powerful sun god. Does anyone know who this is? Ra? Yeah, so the sun god from Egyptian mythology. And on the night side, they wouldn't have a sun god. They don't have a sun, right? So they probably have more stories about the stars or a moon if this planet happens to have one. Does anyone know who this is? Artemis, yeah. Or Diana if you like Roman mythology, but then you're just basically saying you like a stolen and watered down version of Greek mythology. That was harsh. That was harsh. I am trying to influence your opinion in that area. Right. So that was just one scenario, the scenario of tidal locking, but there are, like I said, a lot of other conditions that could exist on a planet. So maybe you want to think about life that lives on a planet that has two suns. That would really influence the stories and the time passage, like the way they measure time. Maybe you live on a planet with a really close planetary neighbor, and so maybe there's this exchange of information between the life forms on different planets, and that would just be an entirely different society, an entirely different culture from what we have. If you live on a planet that's around a really active star, your evolutionary path is completely different from ours because our sun is actually really boring. It's not that active. There are stars that are much more magnetically active than ours. And then there are places in space, there are places in our own solar system where there are a lot more space rocks. So if you live on a planet that's constantly being bombarded by these space rocks, then your life would be very different than ours is here on Earth. And so I've told you how it can influence time and stories, but it can also influence other things that you might not realize, like which sciences become studied, right? The night or the day side of that tidally locked planet might not even realize that astronomy is a thing because they never get to see stars. It influences language, art, architecture, any part of our culture probably is in some way connected back to space because space influences the way our planet forms. And so that's how space touches culture. I'm a really practical person, and so I didn't want to just tell you a bunch of stuff and not tell you why it was useful for you to know. So the first reason that this type of thinking is useful for you is that it's really interdisciplinary. You have to think about sociology, anthropology, biology, chemistry, astronomy, physics, and keeping all of those things in your mind at once and thinking about them and how they interact with each other is a really worthwhile exercise. But second, I think is the second reason this is useful is I think really important for some of the artists in this room. Does anyone know who this is? Who these lovely ladies are? The Muses. Oh, if I had done that in most other audiences, they would not have known who this was. That's great. Right, so you can let science inspire your art. If you're writing a book and you want really funky looking creatures, look at the ocean. There are really funky creatures in the ocean. If you are drawing something and you want a new and interesting shape, look at biology. Look at the cellular structures that exist in your own body because those are really interesting shapes. And so if you're having trouble being creative, you can actually look at science and let that inspire you. And I think that's beautiful. Thanks.
So now we are going to go through a transformation of our own for an exciting final act. So we are going to tidally lock ourselves to that wall. Okay? That means that you're gonna...
This is a super good time to grab a drink.
Yes.
And get up out of here for a second.
Yeah, so go away and come back for a grand and beautiful finale. Now we get to watch two of my very favorite performance artists, Bex and Sophia, part of the Mooncake Collective.
I was on a train a few weeks ago when someone I didn't know approached me. He asked, 请问你是中国人吗? I said, yes, sort of. Clinton, Washington at the stop right now. Yeah, you're on the right train. He looked confused. I'm getting off there, actually. Clinton, Washington, you could get off the train with me? He said again in English this time, you Chinese? I looked over at the couple sitting across from us, and I saw what they were seeing. In that moment, I wanted to be as far away and as close to the stranger as possible.
What's his name?
It's McGraina. Well, also Peter.
Peter Mac.
Mac. Or
Mac.
Yeah.
Peter. Oh. We need to change that photo. That's my dad. Looking very suspicious of your dad. His name is Patrick. Pat. We call him Pat. Kwan. Patrick Kwan. Deacon Pat. Deacon's not his name, but he's Deacon Pat. Han Ming. Kwan Han. Pat. Did you call your dad Peter ever?
No.
Like when you were young and like rebellious?
No, maybe I thought about it. No, but it was mainly Dad.
Dad?
Yeah.
Do you remember when you learned his name?
No, I think I always knew his name because my mom would always yell it when she yelled at him or to him. It was always the whole. It was like McTier. It was always like the whole thing. So I always, but I didn't understand that there was this other name too, this Peter thing, because my mother
she never
said
called Peter.
Yeah. But these days I hear a lot of Mr. Mac, which has been like unusual. Yeah, Mr. Mac. So my dad has been in the hospital, and so the nurses and the doctors will come into his hospital room, and they always greet him Mr. Mac. Hello, Mr. Mac.
hello, Miss Ray.
Yeah, how are you doing today, Mr. Mac? Lovely day out, you know, so-and-so. And then, but it's funny because when they see me sort of like minding my own business in the corner, they're like, oh, and who's this? This must be your, yeah. And I'm like,
are they new? Like, are they every day this happens?
yes, because their shifts are like 12
right,
hours
so there are
long.
many different-
So it's like a new nurse, you know. So when they're like, this must be your, I'm like, I am his child. I'm his child, I'm his kid, and this person here is father of me.
Yeah, with my dad, it's kind of like, he won't let me, or I think doesn't want me or someone else to introduce the me in the conversation. So he will step in early and be like, oh, this is my daughter, kind of,
yeah,
which is odd because he's not like a first speaker, like he's kind of a quiet, more reserved person, and so the fact that he kind of interjects, I always was like, what?
Right.
What's the? And then he'll say like, this is my daughter Rebecca, which he also never calls me Rebecca, so it's this, he's introducing the me that I don't know, kind of. So it's like, what? Oh. And then that stranger's also like, what? So Rebecca? Where? This is my daughter Rebecca, you know? So it's kind of odd.
What does he usually call you though?
But, he used to call me like, he still does, like the middle of my name. So B-E, like that, like, like whatever he's saying, that's kind of a sound that I have come to know as my name. Matt, which sounds like Matt. Right, Rebecca. Because my sisters, what does he call them? I'm the youngest of four, right? So Esther, Deborah, Andrew's my brother, and then Rebecca. We're very biblical, it's just like, just Bible family. Right?
Do those names mean anything?
I'm sure they each have their own meaning. Well, first there was like some alphabetical situation, like Esther. They really started like in the middle. They didn't start at A, right? I think they thought about it later. Maybe they're like, oh, E, oh, D, we're going backwards, okay. And then we skipped C.
And then just went to B.
I don't, A.
R. Oh.
I'm sure. My mom like tried to explain this to me when I was younger. I don't think I quite understood. But Esther, like Queen Esther, powerful woman. Deborah, the judge, the only woman judge. And then I was like, oh, Rebecca, you know, what does Rebecca do? She's Isaac's wife. Like, that's all she really did. I mean, I'm sure she was a really powerful wife. And a person in her own way. But I was always like, I just want a little more. In my name, Rebecca, anyways. It was like spelled differently. It's like B-R-E-B-E-K-A-H. I was really grateful that I was not the K-A-H. I felt like more distance from the wifeness of Rebecca because of that.
Right.
Wait, because Peter was actually one of my father's fellow deacons is Peter. But did Peter think of Peter when he was being, like, when he named himself? Or?
Oh, but yeah. The thing is with my dad is that he didn't name himself. So his name is Goina, not Goina. But he actually, he picked his name out of a hat. So, it was like a day in Hong Kong, a sunny day in Hong Kong. It was like, I think he was 12 or 13. My brother just told me I think he was 12 or 13. There was like a Scottish teacher, and in school. Okay. Yes, and so it was like the day to choose your European name. So in that was like
a hat though?
Yes, there was a hat. So he, I think, has a hat with names in it. And when the hat came to your desk, you just reached in and looked at the piece of paper, and then whatever name was on that piece of paper was the name that you had for the rest of your schooling or your life. And yeah, so it's just this weird thing. So Lorenzio, my dad's colleague, became Lorenzio.
Like that was the name he picked.
Yes, strangely.
Where's this teacher who's writing these names? What was Lorenzio's name? Like Lorenzo original name,
Lorenzio
Chinese name.
was Lo Dunke.
Do you mean Lorenzio?
Yeah. No, I don't think so. Because I don't know how this things. Timothy became Timothy, and then my dad Peter became Peter on that day.
Did he? What do you know if he was like, oh, I've always like that's a great name for me. Like, do you think he looks like a Peter? Look.
You think he looks like a Peter? Maybe glasses make him look like a Peter. I'm not sure.
Like because of the nerdy thing?
Possibly. No, I don't think he looks like a Peter. I don't, when I see his face and then I see the name, I don't see Peter Mac. Always it's written, Goinam Peter Mac, or in English we say Queenang Peter Mac, yes. I don't know.
But-
I think he's,
What were the girl names in the hat?
I don't think there were any girl names because he went to boys' school. So, yeah, King's College, boys' school.
So in those days I was, well actually, I never know how I was born, where I was born. Because in those days people don't tell you about that.
Why?
First, see, in particularly old China, giving birth is not a open thing. You don't tell your kids how you were born for some reason. They always say you were picked up from a piece of rock. See, but since I grew older, I know I was not picked up from a piece of rock. I never know how I was born. I never know where I was born. I was not picked up from a piece of rock.
Thank you all for being with us. Hope you have a wonderful night.
So thank you to our host and all the artists. Please come back next month, June 3rd, for Mariana Valencia. She will host. Have a drink, have fun. Thank you.